Hello, this is Mrs. Scarple, and this is the Lesson 6.4, Part 1, Exponential Growth and Decay Functions video. We begin with exponential growth, which occurs when a quantity increases by the same factor, and when we see the word factor, we need to think multiply, over equal intervals of time. So we're going to multiply a value over and over and over again. This function takes on the form y equals a times 1 plus r to the t. The value of a has to be greater than 0, and the value of r needs to be greater than 0. In the function, y represents our final amount. A is the initial amount, the amount we begin with. R is the rate of growth in decimal form, so any percent increases need to be converted to their decimal equivalent. When you add that rate of growth to 1, you create the growth factor for our function. And the exponent t represents time. So our first example, the inaugural attendance of an annual art festival is 80,000. The attendance y increases by 6% each year. 6% as a decimal is 0.06. You can find this value by moving the decimal 2 places to the left or dividing 6 by 100. Write an exponential growth function that represents the attendance after t years. So we have y equals, our initial value is 80,000 times 1 plus 0.06 to the t power. And we can simplify that sum to have the equation y equals 80,000 times 1.06 to the t. So when we look at part B, how many people will attend the festival in the 5th year? Round your answer to the nearest 1,000. So in our calculators, we can actually enter, just as I'm writing here, 80,000 times 1.06, but we'll change that t to a 5 for 5 years. And as I mentioned, you can enter this in the calculator just as it is written. And you should end up with a number that is approximately 107,058. But our directions did say to the nearest 1,000. So we have 8 in the ones, 5 in the tens, 0 in the hundreds, 7 in the thousands. So to the nearest 1,000, this is approximately 107,000 people in attendance. Exponential decay decreases by the same factor over equal intervals of time. The only difference between the exponential growth and the exponential decay functions is that in the exponential decay, you're going to subtract that rate of decay. And because we are subtracting the rate of decay, our growth factor will actually be less than 1. If you notice the last problem, when we increased, our growth factor was 1.06, which is more than 1. When it comes to a decay, this value here will be smaller than 1 because we are subtracting from 1. So we're going to determine whether each table represents an exponential growth function, an exponential decay function, or neither. So as long as our intervals of time, or x, are the same, we can look to see, is there something I can multiply by to get my next value? So 24 to 12. Well, I know 12 is half of 24. Many of you may be thinking, well, that's a division. But keep in mind, we can write division as times 1/2. If I take 12 times 1/2, I will get 6. And if I take 6 times 1/2, I will get 3. So our growth, or our decay factor actually, is going to be 1/2 because everything is getting smaller by 1/2. So this is decay. And I should mention exponential decay because we are multiplying by 1/2 every time. For B, again, we have the equal intervals. So if I look at my growth, 4 to 40 is times 10. 40 to 400 is also times 10. And 400 to 4,000 is times 10 as well. Because we're multiplying by that consistent factor of 10, this becomes an exponential growth because we're getting bigger. Example 3, we can also tell by looking at equations whether they represent exponential growth or exponential decay. And once we've done that, we're going to find the percent rate of change. So because this is greater than 1, this is going to be exponential growth. To find the rate of growth, we know that 1 plus r has to equal 1.09. So to find r, which is that rate of growth, I'm going to subtract 1, and r is going to be 0.09, and as a percent, that is 9%. B, we have 24 times 0.93 to the t. This 0.93 is less than 1, so this is exponential decay. To find the rate of growth, or actually rate of decay in this case, we know that 1 minus r has to equal 0.93. So I can subtract 1 from each side again, and I'm going to have negative r equals negative 0.07. So if I divide both sides by a negative 1, I get that r is equal to 0.07, or a 7% decay. In example 4, we're going to rewrite each function to determine whether it represents exponential growth or an exponential decay. We're going to have to rely on our properties of exponents in order to do this rewriting. So we have y equals 20 times 0.81 to the t over 2. Another way I can write that t over 2 is that it's 20 times 0.81 to the 1/2 times t. And if we think about when we would multiply exponents, it would be when we have the exponent on our base. So I'm going to write 0.81 to the 1/2 and take it to the t power. So I need to calculate what is 0.81 to the 1/2 power to determine whether it represents exponential growth or an exponential decay. So in a calculator, when you do that exponent, you're going to want to do 1 divided by 2 as that exponent. So we have 0.81 to the 1/2 is going to equal 0.9 to the t. Because 0.9 is less than 1, we can say that this is exponential decay. When I look at example B, we have t minus 2. If you remember your properties of exponents, we would subtract when we have a quotient. So this right side of my equation is going to become 2.5 to the t over 2.5 squared. And when I find 2.5 squared, I'm going to have 2.5 to the t divided by 6.25. Another way I can think of this, because I need the 2.5 because it's taken to the t for time, I can think of this as 1 divided by 6.25 times 2.5 to the t. And to find out what that initial value is, I need to divide 1 by 6.25. So 1 divided by 6.25 is 0.16 as our initial value times 2.5 to the t. Now when I look at this, I see that 2.5 is greater than 1. That makes this exponential growth. So if you have t divided by 2, that's going to be 1/2 times t. If I had something like 2t, I would still do like I did with this 1/2. I would move it inside with this base value and evaluate it to determine if I have growth or decay. When I have t minus 2, it's going to be a quotient. If it were to be t plus 2, I would have a multiplication. So think about how those properties of exponents work to help you when solving these to find that rate of decay or that rate of growth.